The energy carried by the electrons is derived by the materials of the oxidizing and reducing agents, as well as other factors including temperature, pressure, solution concentrations, and so on. The better able the reducing agent can lose electrons at the anode, and the better able the oxidizing agent can gain electrons at the cathode, increases the separation of charge between the two electrodes. The difference in charge between the two electrodes is called the electrical potential difference and is measured in volts. For any given cell, the electrical potential difference between two electrodes is called the cell potential. The standard cell potential is an internationally agreed set of standard conditions for reporting cell potentials. The cell potential is the difference in energy of the electrons between the anode and the cathode. If we were to arbitrarily set one of the electrodes to have an electrical potential of 0, the voltmeter measures the difference between the two electrodes, and that voltage becomes the cell potential. Let's try to illustrate this last point. Let's say we arbitrarily set the copper half cell to have a half cell potential of 0 volts. That is, we make it the reference half cell. The voltmeter reading would be 1.10 volts as the standard cell potential. We'll get into where the actual numbers come from in a moment. Since the cell potential is the difference between the two half cells, that makes the half cell potential for the anode negative 1.10 volts. This is the equation you need to remember. Cell potential equals the half cell potential of the cathode minus the half cell potential of the anode. This is why the anode is negative 1.10 volts, so that the voltmeter would read a positive number. All voltaic cells have positive cell potentials. Your data booklet lists a table of selected electrode potentials. These are the numbers on the right side of the table of reduction half reactions. These voltages have been measured under standard conditions. The half-cell potentials of the half cells listed here are defined as the potential difference between any one of these half cells and the hydrogen half cell. Chemists have agreed the hydrogen half cell be the reference half cell to which all other half cells are related. In this voltaic cell, the zinc electrode is being oxidized and the hydrogen ions are being reduced at the platinum electrode. In this case, hydrogen gas is being released. The half-cell potentials from your data book enable you to calculate the voltage of the cell. Using hydrogen as one of the half cells, this is pretty easy to do. In this voltaic cell, the hydrogen gas is being added, then oxidized, forming hydrogen ions in the solution. The copper-2 ions are the stronger oxidizing agent. For the hydrogen half cell, hydrogen gas acts as the reducing agent for the oxidizing agents listed above it in your data book. And the hydrogen ions act as the oxidizing agent for the reducing agents listed below it. Since this table shows reduction half reactions, the half cell potentials are frequently referred to as reduction potentials. This reduction potential for this half reaction, as read from your data book from left to right, is negative 0.13 volts. This is the oxidation half reaction, the same reaction read from your data book, this time from right to left. The oxidation potential has the same voltage, but the opposite sign. When calculating the cell's net potential, you are adding the reduction potential that occurs at the cathode to the oxidation potential that occurs at the anode. Since our data booklet only lists reduction potentials, you can still use those values, and the negative sign in the formula takes care of the opposite sign of the oxidation potential. Here's an example. What would the cell potential of the Daniell cell be under standard conditions? The diagram indicates which is the anode and which is the cathode. But even if it didn't, you could still use your data book to determine what is being oxidized and what is being reduced. For voltaic cells, the reaction will proceed spontaneously. First, we write the reduction half reactions involved with their reduction potentials. Using this formula, substitute the E cathode for the reduction potential of the strongest oxidizing agent and E anode for the reduction potential for the strongest reducing agent. In case you're wondering, since the reduction potentials given are both related to the same reference half cell, we can go ahead and use these values in the equation. I'll expand on this point a little later. The positive value confirms the spontaneity of the reaction. We'll discuss the negative E cell's values later. It's important to note that having the hydrogen half cell in the reference cell only establishes the values of the reduction potentials for the two half reactions. If the reference half cell were anything else, the reduction potentials would be different, but at the end of the day, the electrical potential difference between the two electrodes would still be exactly the same.